In this video, I'd like to discuss the end behavior of polynomials. Now, if you look at a definition of end behavior of polynomials, it looks a little overwhelming. Look at all this stuff. Look at all these words and all these funny symbols. But essentially, the key to end behavior of polynomials, the really bottom line is that it helps us to understand how a function like this guy here relates to its graph, like this guy here. That's what end behavior of polynomials really does for us. It helps us to relate between this guy and this guy. I'm hoping by the end of this video that you can look at something like this and match it up with its graph that looks like this. Or you could look at a graph that looks like this and match it up with its equation or its function that looks like this. Now, part of matching up a function with its graph or a graph with its functions is this bottom part here, the part that says real zeros of a polynomial function. This definition, let's take a quick look at it. The maximum number of zeros of a polynomial function is equal to the degree of the polynomial. Okay, good to know. Zero of the function is a point at which the graph intersects the x-axis. I hope you already knew that. On a graph, count the number of real zeros of the function by counting the number of times the graph crosses or touches the x-axis. So, okay, so this is great. This is a good definition that helps us to understand how the crossings of the x-axis relate to the degree of the polynomial. That's good to know. Why don't you take a moment and write this down? You can summarize it in your own words, and we'll be using this later. But just to be clear, don't write this part down. Don't write this part down. I'll show you an easier way to remember that stuff. So the good news is, if we have to remember something about end behavior of polynomials, there's only 4 basic categories of things that we need to remember. First of all, polynomials have degrees, and I'll show you what those are in just a second. Maybe you can. The degree of the polynomial is simply the highest power of any variable in the polynomial. So in this case, this particular polynomial it's known as a 4th degree. This guy is the degree, and so we would call this polynomial a 4th degree or a degree 4 polynomial. Now, notice that it's the highest power of any variable in the polynomial, not necessarily just the power of the first term. Of course, since I am mentioning the first term, let's go ahead and put these guys in order. Technically, this should be 7x to the 4th minus 3x squared plus 5x minus 2. And when we put this guy in this order, we can talk, there's a special name for this first term, the term that has the highest power of any other variable. And that special name is this guy is called the leading term, And just to be clear, the reason why that guy is called the leading term is because this is a term, and this is a term, and this is a term, and this is a term. Hopefully you remember from your vocabulary that things that are added together or subtracted are called terms. So this polynomial has 4 terms in it. All right, let's get back to the leading term here. The leading term has a couple of things that we're interested in. It has this part right here, which we already said we call that the degree. But there's something else that's really important about the leading term, and that is this part right over here, this number. This number has a name. It is called the leading coefficient. If you want to understand end behavior of polynomials, then there's 2 things that you really need to understand. One of them is the degree, and one of them is the leading coefficient. So we'll go back to our table and we'll fill it in with these 2 things in mind. So if degrees and leading coefficients are what we're concerned about, then over here on this part of the table, we're going to say this represents leading coefficients. Now, it turns out that we have two kinds of degrees and two kinds of leading coefficients. We have odd degrees and we have even degrees. And let's just take a quick look at examples of those. So, in this particular case, since the degree of this polynomial is a 4, that's known as an even degree. Since this leading coefficient is positive, it's positive coefficient. So let's take a look at another couple examples. Here's an example of an odd degree polynomial because the degree is 5, and that's an odd number, and it just also so happens to have a negative leading coefficient. We'll look at that in just a minute. So polynomials can have odd degrees or even degrees, and they can have positive or negative leading coefficients. And in this handy dandy little table, we're going to document at least what they look like. So let's do that real quick. If this is an x-axis and this is our y-axis, and we call this guy a coordinate plane, if we have an odd degree polynomial with a positive leading coefficient, on the right end of it, it'll be as we go to the right, it's going to go up, and as we go to the left, it's going to go down. That is what an odd degree positive leading coefficient polynomial looks like. If we have an even degree polynomial that has a positive leading coefficient, it's going to go up on the right, and it's also going to go up on the left. We've seen both of these guys before. This is an example of a linear equation, which we should not be too surprised might very well have a odd degree. Remember, y equals x to the power of 1, and definitely a positive leading coefficient. And this other guy we've seen before as well. This is it's a parabola for a quadratic, and so again, it would have maybe a positive leading coefficient of 1, maybe not this guy, and it would have a degree of 2, which is even. So even with positive leading coefficient. So the good news is that we've seen this stuff before. We've seen odd degree polynomials with positive leading coefficients and even degree with positive leading coefficients. It just turns out that there's this rule that says for every polynomial with an odd degree and positive leading coefficients, it's going to look a little bit like this on the ends. Only on the ends. So on the right and on the left, odd degree polynomials will look like this guy. Now, before I go too much further, let me show you an example so that you know what I'm talking about. So when I say that an odd degree polynomial with a positive leading coefficient, here's a positive leading coefficient, let's make it an odd degree, so power of 3. I want you to notice that it goes up on the right and down on the left, sort of like the positive linear equation that we've studied in the past looks like. So when we saw something that looked like this, 2x plus 5, let's say, notice that as it goes to the right, it's going up, and as it goes to the left, it's going down. I'll zoom out a bit so you can see it. So it's going up to the right, down to the left. It turns out that this is true also. Again, all odd degree polynomials with positive leading coefficients will go up as you go to the right and down as you go to the left. All even degree polynomials go up on the right and up on the left as well. You might ask yourself, to the left of what? Well, or to the right of what? Well, it's not really to the right or the left of any specific thing. It's just as x gets really big, as x goes to positive infinity, we're concerned about what happens with f of x. So as x goes to positive infinity for even degree, positive leading coefficient polynomials, we say that f of x also goes to positive infinity. In other words, a very large number in this direction. And then the other thing that we say is that as x goes to negative infinity, in other words, and this is a little confusing because really we're talking about going in this direction. This is negative infinity this way. As x goes to negative infinity, f of x just happens to go to positive infinity. There we go, to positive. And what do I mean by that? Well, as the x values get very large, the y values, as the x values get very negative, the y values get very large in a positive sense. So this is sort of the algebraic description of the pictures we see. And again, this is true for all even degree positive leading coefficient polynomials. So let's take a look again in Desmos just to verify. So let's take a look at a positive leading coefficient. I'll try 4, and we'll try an even degree polynomial like to the 4th power. Actually, let's make that leading coefficient 5 so it's different. And then even degree polynomial, we can see that as we go to the right it's going up, and as we go to the left it's going up. Now we could see this a little more clearly if I could zoom in on these x values between maybe -2 and +2, and maybe go up higher so that we can see more y values. So I'm going to change my y's to go from -2,000. Actually, we'll just go from 0 on this one, all the way up to we'll go to 2,000. So we'll go to a very high number, and then our x's will just go from maybe -3 to +3, and let's see how that works out. Oh, even that it doesn't fit perfectly. There we go. So we can see that for this positive leading coefficient even degree polynomial, we can see that we go up on the right and up on the left, just like what we saw in the diagram here. So every even degree polynomial will act similarly to the quadratics and the parabolas that we've already seen. They go up as we go to the right, and they go up as we go to the left. Of course, let's finish this off with what happens with negative coefficients for odd and even degrees. For odd degree polynomials, if we have a negative leading coefficient, we get something like this. On the ends. We're not saying there's no squiggles in the middle. So let me be really clear about this. We go up as we go to the left, and we go down as we go to the right. But in between, anything could happen. We could easily have something that looks like this, and that would still be considered an odd degree polynomial with a negative leading coefficient. And also for even degree with negative leading coefficient, we could see something that goes down like this as we go to the left, and it goes down as we go to the right, and in between there could be a whole bunch of stuff, and there could be squiggle, 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 and then such. All we're really concerned about with end behavior of polynomials is what happens on the ends. Now, what I'd like to do is I'd like to put in a description of what happens to f of x for every one of these situations. So I'm going to go ahead and start filling in the rest of the chart with this stuff. And what I'd like you to do is when you think you've got it, I'd like you to pause the video and try to fill in the rest on your own instead of just copying what I write. So I'm about to write what happens to f of x as well. First of all, I guess I'll start you off here. As x goes to positive infinity, I'd like it if you could write what happens to f of x. And over here, same thing. As x goes to negative infinity, I'd like it if you could write down what happens to f of x. So you're going to pause the video, and if you can, that'd be great. If you can't, then in a minute I'll show you how to do this. Alright, so here is my take on this. As x is going to positive infinity, f of x is also going to positive infinity. Here, as x goes to negative infinity, in other words, as x goes this way, then what happens is f of x is going down to negative values, so we call that to, we say f of x is also going to negative infinity. All right, let's try this again with this guy. Now, if you want, you can go ahead and get started without me. You can go ahead and pause, or at least I'll give you a little head start. Again, what we're concerned about is as x goes to positive infinity, what happens to f of x? Maybe you could fill that in. And then the same thing over here. As x goes to negative infinity, what's happening to f of x? I'd like to know. Why don't you pause the video, see if you can fill this in. All right, here's my take on it. As x goes to positive infinity, f of x is going down, so we'll say that means it's going to negative infinity. And then over here, same thing. Let's see, as x goes to negative infinity, as x goes this way, looks like f of x is going up. So let's go ahead and let's write what that is. F of x must be going to positive infinity as x goes to negative infinity. All right, one last one. It'd be great if you could fill this whole one in all by yourself. If you hit the pause button, go ahead and try it. Otherwise, I'm going to get started. As x goes to positive infinity, and then as x goes to negative infinity, give you guys a little head start so that you can try it on your own. Over here, f of x must be going to negative infinity, and over here f of x is also going to negative infinity. All right, so sorry about all the positive and negative infinities. That does kind of make this a little bit messier, but I will say this. This table, if forget about all the positive and negative infinities, this is a really useful table. And so what I would really like you to do is, regardless of all that positive and negative infinity stuff, this table, as you see it here, I would love for you to recopy this table, and when you do, this is what I'd like you to memorize. And I will tell you this. My hope is that this table, if you write it down in this order, I'm hopeful that it's actually easier to remember which types of polynomials have odd and even degrees. Now, the best thing we can do now is try practicing with a few examples. So let's see what happens.